Hello, everyone. Welcome to the last session of Wednesday. The first speaker is Cambyse Rouzé. He's currently with the Technical University of Munich, and he is also the co-authors of the next two talks. Today, he will talk about quantum transport entropy inequalities. Cambyse, the floor is yours.
I sorry, I don't know if it's my connection or yours, but I cannot, I only hear a few words that you said.
So, I think you can start anytime.
Hello?
Yes, can you hear me? Cambyse, you can start.
Okay, great. Sorry, I just saw the message. Okay, thanks a lot, Hao-Chung. Sorry, I didn't hear what you said so far, but let me thank also the organizers for giving me the chance to present my work at this nice workshop. So as the title suggests, in this talk, I will present some recent progress in collaboration with Giacomo de Palma on some inequality which relates two concepts. First, the concept of quantum optimal transport, which has been the focus of quite a lot of attention in the last few years. And on the other hand, the concept of quantum entropy, which is, of course, a much more well-established notion in the community. But before I just give you the inequality and tell you where and why it is satisfied, I would like to motivate it with some problem from the foundations of statistical mechanics. So this problem is the one of the equivalence between statistical ensembles, and in any textbook on the field, it is usually described as follows. So if you have a quantum system sigma, which is in contact with a large path B, and if you take the union of those two systems and assume that they are isolated, then this union will basically evolve unitarily with a unitary which is generated by some Hamiltonian. And you can always decompose this Hamiltonian into three terms. So first, H sigma, which basically encodes all the interactions that occur at the level of the system sigma itself. Then HB, which encodes the interactions within B itself. And then HI, which is basically encoding the interactions between sigma and B. Now, at equilibrium, there are different ways of modeling the state of your system sigma. And each of those ways are usually referred to as statistical ensembles by physicists. So in the microcanonical ensemble, you will assume that you know that the energy of the universe, so the system and the bath, is at some fixed energy capital E, which you know within some precision capital delta. And so the way to model the state of the full system is to take the uniform mixture of all the eigenstates of energies that lie within this interval. And so the state of the system will simply be the reduced state to that one. And on the other hand, in the canonical ensemble, so the state would be defined as a Gibbs state in the sense that it's exponential of minus some inverse temperature of the bath times the Hamiltonian of your system itself, divided by some normalization constant, the partition function. And the natural question to ask is whether there is a way to relate those two descriptions. And the answer is yes, in some cases. So if you take the limit, the thermodynamic limit, so by this I mean the limit of a very large path, then as long as the interaction Hamiltonian HI is very small as compared to the other Hamiltonians, then you can pick a suitable choice of inverse temperature, which depends on the energy of the universe, such that in that limit, the two states converge to the same state. So you can also think of this kind of meta result as providing the temperature with some statistical meaning or statistical definition. Now, this condition that the interaction Hamiltonian is very small as compared to other parts of your Hamiltonian is usually very restrictive. And one place where we do not want to assume this is when you take the system to be simply some region of a larger system. And so there's no reason why the interactions between that region should be much smaller than other kinds of interactions occurring at the level of the whole system. So to be more precise now, in this talk, I will consider a system that is defined through a hypergraph, which is a set of vertices. So for each of those vertex V, I will append some quantum qubit system, and there will be a small n of them. And the hypergraph is also defined through a set of regions or hyperedges, which basically encode the information about the possible interactions between those vertices, so that the Hamiltonian of the full system will be a sum of those terms, HA, where for each A, the support of HA is exactly equal to the region A. And now the question we want to ask is slightly different from before. We want to find some conditions, natural conditions, under which the canonical ensemble state of the full vertex, of all the vertices, is in some sense going to be close to the microcanonical ensemble state for the full system as well, for some given chosen parameters, beta, E, and delta. And to give you some intuition for why this could potentially be true, let's consider a local Hamiltonian defined on, say, a regular two-dimensional lattice system. And since it is local, obviously the average of the Hamiltonian in the Gibbs state will scale linearly with the number of particles. But I will also assume that the Gibbs state has some exponential decay of correlation. So we just saw this notion in the previous talks yesterday. So that means that if you take two separated regions of your lattice, the correlations measured in the Gibbs state will decay exponentially fast in the distance that separates the two regions. And if you assume this, you can easily prove that the variance of the Hamiltonian will also scale linearly with the number of particles. So now we have a condition on both the first and the second moments of this Hamiltonian, and we can use basically Chebyshev inequality to prove that the energy density will concentrate around the average. So this is what I'm trying to explain in this figure here. So in the Gibbs state, the density of energy will have a profile that could resemble this and concentrating around the mean. That also means that you can approximate this curve by some step function that is also concentrated around the mean and of some width that is going to scale, say, sublinearly with the number of particles. For example, you can take it to be as a square root of n. So this is kind of giving us an intuition that since those distributions, when you measure the state in that Hamiltonian in the states are close to each other, maybe the states themselves would also be close to each other. And so the answer to this question is, well, this will depend on the measure of distinguishability that you're assuming on your states. And if you want to look at the overlap between the states, so this would be like a global measure of distinguishability, then for any kind of natural parameters, beta, energy E, and width delta, you can prove that this overlap will actually exponentially converge to zero in the limit of a large number of particles. So that kind of tells us that we need to look at some more local notion of distinguishability. These global notions will not work. And so the idea now is to find a class of observables, O, such that indeed the average of the observable in the canonical state ensemble will be close to the average in the microcanonical state ensemble. So this kind of line of thoughts was, I think, first introduced by Lima back in the 70s. And more recently, from the quantum information community, people like Müller and Carruthers came back to this problem. And what they could prove is that if you impose your graph to be a regular lattice of dimension d, and your Hamiltonian to be local and translation invariant, then under the condition that there exists a unique Gibbs state in the thermodynamic limit, so in the limit n goes to infinity, you can indeed approximate all those local observables, so observables which are supported on a fixed small region of your lattice. So in those observables, these two expected values will be the same in the limit n goes to infinity, so in this asymptotic regime. as long as the shell defining your microcanonical state ensemble is not too small, and if you take it to be a small fraction of the total number of particles, then you can prove the equivalence between those two expected values. So now this idea was refined later on, and in particular in the work of Brando and Kramer. So what?
Sorry, Cambyse, may I interrupt?
Of course,
please?
Yes.
Can you explain what you mean by the shell there, please?
Oh, so this remember this microcanonical state ensemble ensemble state was defined according to by taking the uniform mixture of all states which lie within this the interval E minus delta E. So this is what I mean by the shell.
Okay, fine, thanks.
Thank you for the question. So so in the work of Brando and Kramer, they managed to prove that under the condition of exponential decay of correlations in the Gibbs state, they could prove a bound on the difference between these two expected values, of course, which would depend on n and which would go to 0 as n goes to infinity, for a slightly more general class of Hamiltonians. So they could remove this condition of translation invariance. And more interestingly, they could assess observables which are not only local, but actually supported on possibly microscopic regions. So as long as the size of the region where the observable is defined is not scaling bigger than n to the power of 1 over d plus 1, their result was also holding. And they could also improve over the shell. So the shell could actually be much smaller, exponentially smaller than before. And the way they could prove this was to prove some some strong concentration inequalities for the Gibbs state, and namely the Berry ascending in their setting. And so this idea of using concentration inequalities was then further developed by Kuwahara and Saito. They have several articles on this, but here I just mentioned one of them. And in this article, they could prove that they can first relax this condition that the graph is a regular lattice. They could look at arbitrary lattices. And they could prove in this framework that as long as you're above some threshold temperature, they can get a bound on the difference between those two expected values, just like before. But now they can relax the locality assumption on the Hamiltonian. So they could look at few body long range interactions. And the same for the class of observables. So this class is not necessarily bigger than the previous one, but it's just a different class of observables. And one notable difference with the previous result is that they could take the shell now not only to scale weakly with the number of particles, but actually to go to 0 very fast, exponentially fast. They can take a very, very small shell, and still the two states would be essentially the same when you measure them against those kind of observables. And so now our result can be seen as a one step beyond this previous result. So we get essentially the same kind of dependence as Kuwahara and Saito, but for a more general class of observables, which are what I would call Lipschitz observables. And we'll get back to this notion in a second. But for the time being, you can think of this as extending all the previous classes. However, at the time being, we have to restrict ourselves to commuting Hamiltonian. So this is a condition that we would like to get rid of, but for the time being, we don't know how to. And here's finding the connection to the title of my talk. The proof that the technique that we'll use to prove this result will go through this transport-entropy inequalities. And so, as I will mention in a second, these transport-entropy inequalities are basically very much related to this notion of concentration of Gibbs states. And in fact, classically, the notion of Gaussian concentration, which is what Kuwahara and Saito were using in their proof, and the notion of transport entropy are equivalent to each other. So what do I mean by this? By Gaussian concentration, I mean the property of a measure mu defined on a metric space, omega with a distance d, according to which for any function f from that metric space omega to the reals, the probability that f deviates from its mean by some parameter t can be controlled by twice the exponential of minus t squared over some constant c times the square of the Lipschitz constant of the function. And so this turns out to be equivalent to what I will call a transport entropy inequality, which states that fixing the same measure as before mu, for any other measure nu that is absolutely continuous with respect to mu, the Wasserstein distance between those two measures is controlled by the square root of that same constant c as before, times the relative entropy d of nu mu. Okay, so what is this Wasserstein distance now? It is defined as the difference of the expected value of a given function in the measures mu and nu, and then maximized over all those functions which have a Lipschitz constant less than or equal to 1. So we all know a very simple example of a Wasserstein distance. If you take the underlying metric D to be the trivial metric, which will assign 1 to any 2 points of your sample space when they are different from each other, then you recover the total variation distance. And so this transport entropy inequality just reduces to Pinsker's inequality. But we want to look at different classes of Wasserstein distances. And in the setting of spin systems, the more natural underlying distance that we want to take, which will keep the kind of the locality structure of your spins, would be the Hamming distance. The Hamming distance between two configurations of spins simply measures the vertices where the spins will differ from each other in these two configurations. And now the idea is so we want to prove that for any Lipschitz function in this classical setting, that has a Lipschitz constant less than some parameter k that does not scale with n, the density of f average over the canonical ensemble measure is close to the density of f average over the microcanonical ensemble. And using transport entropy inequalities, we can prove that this will be true, this will be satisfied as long as the Gibbs measure satisfies transport entropy with a parameter little c that scales linearly with n. And as long as, yes? So I could hear something. Okay. And as long as the relative entropy between those two measures scales sublinearly with n. So this is kind of the strategy we want to follow also in the quantum setting.
Cambyse, where will the k dependence come in, right? There should be some k dependence, right?
Yes, sorry, there would be a k here, indeed. I want to take the k to be just a constant here, so but you're right, the k should be as a factor of the right-hand side here. But the important part is that it should not scale with n. So you can just reabsorb it in the constant c if you want.
Okay, thanks.
Thanks for your question. Okay, so this is kind of the idea. And since we want to extend this to the quantum framework, we need to introduce a good notion of Wasserstein distance on quantum states. And there are by now various definitions out there, but the one I will focus on is the one that was defined by Giacomo de Palma and his co-authors last year. So again, it is a difference of expected values of some observable O in the two states that you're considering, rho and sigma, and then maximized over those observables which have a Lipschitz constant less than or equal to 1. And okay, so by a Lipschitz constant of an observable, I mean the following quantity. So you're taking the distance of your observable from this set of observables which are supported everywhere on your vertices, but on the vertex V in the operator norm, and then maximizing over your vertices. So this might look a bit odd at first glance, but the reason why they introduced the constant as follows is because first it recovers the classical definition. So if you take the observable to be a diagonal in the computational basis with eigenvalues which are defined through a function of your classical spins, then the Lipschitz constant of the observable will be exactly equal to the Lipschitz constant of the function with respect to the Hamming distance. And as I mentioned before, I want this class of Lipschitz observables to be larger than previously considered classes. So for instance, it will be larger than the class of local observables. So if O is a sum of OIs, where each of those OIs have a norm bounded by 1, say, and they are supported on small regions of the lattice, which do not scale with n, then also you can prove very easily that the Lipschitz constant of O will not scale with n. But you can also assess much more general classes of observables. So if you take, for example, O again to be a sum of OIs, with the same condition on the strength of those OIs, but now you can allow yourself for the supports of the OIs to be actually very large and to scale with n. Then as long as those supports do not overlap, you can again prove relatively easily that the Lipschitz constant of the observable will not scale with n, even though the supports of those OIs might scale with n. Okay, and to give you a bit more intuition to what is this Wasserstein distance, it's also nice to see how it compares to the trace distance, I think. So you can always lower bound it by the trace distance. And you can also get an upper bound with a coefficient of equivalence, which will be the cardinality of any set where the two states will be the same on the complement of that set. So in that sense, this is kind of saying, okay, this Wasserstein distance also has this kind of, it will be it will provide you with a local notion of distinguishability between quantum states, a bit like the Hamming distance was providing you with a local measure of distinguishability between classical spin configurations. Okay. So following the strategy, we want to prove transport entropy for Gibbs states. And one thing to perhaps do first is to see what is known about Gibbs measures, so in the classical setting. And in the classical setting, it is known that a Gibbs measure will satisfy transport entropy inequality with a constant scaling with n, like we want, under at least two conditions that I know of. The first one is holds for arbitrary graphs, and as long as you are above some threshold temperature. And this is what I want to quantize in this talk. But there's also another way to prove those on regular lattices under the condition that the Gibbs state has exponential decay of correlations. And the way to prove the implication from this condition to transport entropy would be to go through a notion of log-Sobolev inequality, but I will not mention this further in this talk. I invite you to follow the talk of Angela Capel after this one if you want to know more about those beasts. Okay, so I will focus on quantizing this first step now. Just to remind you again of the framework, we are looking at a Hamiltonian, which is a sum of HAs, where the support of those A's are some regions of your vertices. And as I mentioned before, I will unfortunately have to impose that those HAs commute with each other. So that's something that we would like to get rid of, but for the time being, we cannot. And the Gibbs state will just have this expression as a function of the inverse temperature. Now, here's finally our main result. So we prove that just like in the classical case, above some threshold temperature, for any state rho, the Wasserstein distance between rho and your Gibbs state sigma can be controlled by the square root of this constant times n times the relative entropy between rho and sigma. So this constant would be a function of the inverse temperature, as well as this capital N, which you can think of as just measuring the locality in your Hamiltonian in some sense. And for 1D lattices, we can actually prove that the inequality always holds for all strictly positive temperatures. Okay, so now I mentioned before that there is classically an equivalence between transport entropy and Gaussian concentration. And then you can still prove one implication in the quantum setting. So we can prove that if a state sigma satisfies transport entropy inequality, then for any observable O of your vertices, the probability under that state that the observable deviates from its mean by some parameter r can be controlled in the following manner. So you get again a sub-Gaussian tail for this probability. And the difference with the classical bound lies here. So the Lipschitz constant will not only depend on the observable, but you have to actually take into account the Lipschitz constant of a modified version of the observable, which also depends on the state. And that's something I would be very interested to know if this is actually required, or if this is really just because of our proof technique, but so far we cannot do better than this. But at least when those two, the observable and the state, commute with each other, then we do recover exactly the classical bound. And that's also a condition that might seem very strong, but if you want to assess the distribution of the Hamiltonian, then of course it will commute with the state, and then you do recover the tightest bound you could expect for. And I would like to also compare this with previous Gaussian concentration bounds in the literature, and in particular the one that Kuwahara and Saito used to prove their equivalence of ensembles. So as I told you before, they were considering a larger class of Hamiltonians, namely those which are sums of OAs which are supported on k vertices, which might not be close to each other. But they also had to restrict themselves to observers which are also belonging to the same class. And so under this condition, they could prove again also some kind of Gaussian bound. However, the range of temperature in which their result held depended on the k here. So the number of vertices where the observable has to be supported. And in particular, when k grows, and if k grows with n, then the bound, the interval becomes trivial. So for this range k too large, our bound would be much better. Of course, this comes at the cost of having to look only at commuting Hamiltonians. Okay, so now let me first wrap up with our result on the equivalence of ensembles. So we prove indeed that above the same threshold temperature where this transport entropy inequality holds, for all observables O of Lipschitz constant bounded by some k independent of n, the density of O average in this Gibbs state minus the density of O average in the microcanonical state will go to 0 as n goes to infinity, as long as you choose your shell to be at least scaling like exponential of minus the number of particles. And as I told you before, so the proof goes through first proving that the Gibbs state satisfies transport entropy. So this is already checked from the previous slides. And we only need now to control the relative entropy on the right-hand side of this transport entropy inequalities. And to do this, we will follow just a standard method. So first, we will pick the energy to be maximizing this quantity. So the exponential of minus the inverse temperature times E times the number of eigenvectors which lie within whose eigenenergies lie between E minus delta and E. And so imposing E to satisfy this maximization problem, we can prove using the concentration bound for the Hamiltonian that this relative entropy will indeed be controlled in terms of the relevant parameters of the problem. And since we have a logarithm here, this is exactly what allows us to take this energy shell to be very, very small. And you can just plugging in this expression for delta, you can see that indeed this relative entropy will be scaling sublinearly with n. And so this kind of finishes the proof of this theorem. And I think I have just enough time to give you a few details about the proof of the transport entropy inequality. So the idea is we want to use Pinsker basically. So we know how to relate the Wasserstein distance to the trace distance. And then we know how to relate further the trace distance to the square root of the relative entropy. And however, since we want this inequality to hold for all states rho, and in particular for those states which might be different from sigma on all the vertices, if we were to use directly this bound straight away, the best we could do was to get a bound that depends linearly on n. And so if we use Pinsker afterwards, we would get the n outside of the square root. So this would be too rough for our purposes. So now the idea is to, instead of just using directly Pinsker, is to locally modify your state rho into the state sigma. So what I mean by this is that we can introduce some average Petz recovery map, so average over all the vertices. And so for each vertex, what you do here is to replace the state rho locally on the vertex V by the state sigma. And to do this, we use these rotated Petz recovery maps, which we already mentioned yesterday. So you can just think of this as a local map which acts on your state locally and replace the information on rho by the information on sigma. And let me just denote this composition of maps by psi v now. And so this map, this global map R now is what I would call a Gibbs sampler in the sense that it takes any state rho, and if you apply the map many times on this input state, you will converge to the Gibbs state. So now we will use this map on the left-hand side of our transport entropy inequality. And by triangle inequality, we just control this initial Wasserstein distance in terms of the Wasserstein distance between the state at the output of I application of your channel and the one at the output of I+1 application of the channels, plus some remainder term. And notice here that the letter n, the number of times we are applying the channel, is exactly equal to the cardinality of my set of vertices. And now what we can prove is that this Wasserstein distance, of course, should be smaller than the previous one because we know that the state rho in some sense converges to sigma. But we can actually prove that it will contract. So above some threshold temperature, this Wasserstein distance will be smaller than some parameter epsilon that depends on beta, that will be strictly less than 1, and independent of n, that's the important bit, times the initial Wasserstein distance. So this is actually where most of the analysis goes, but I won't have time to explain further here how to do it. But the point is that once we have this, we can just put this term on the left-hand side of the inequality. And the only thing we need to control now is this sum in terms of the square root of the relative entropy. And to do this, we further expand the sum using the locality structure of our channel R here, so that in the end, we're just left with having to control the Wasserstein distance between some state rho and the state where we applied this local channel psi v. So now we can use in a much more refined manner this control of the Wasserstein distance by the trace distance. As I mentioned before, this state will be almost the same as the previous state up to maybe some neighborhood of the vertex v. So we can control this locally by the trace distance between the two states. And then the rest of the proof just goes as you would expect. You spin square inequality here, then some recovery bounds, and then you can just wrap up all things together, and you get indeed a bound on the sum of the Wasserstein distances in terms of what you wanted. So the square root of n now times the relative entropy between rho and sigma. Okay, so I think I'm reaching the end of the talk. So just to mention a few directions. So I would be very interested to know if this kind of transport entropy inequalities, which you can think of as refinements of Pinsker, basically, could be used in other places of quantum information theory. And we have already a place where it can be used to learn, to devise some efficient learning algorithms to learn Gibbs states at high enough temperature. And this will be the subject of the talk of Daniel, I think, on Friday. And you will see also today by the talk of Tristan Benoit that using some other kind of inequality relating the Wasserstein distance and something else in the relative entropy, you can also get concentration bounds not for the Gibbs state, but for the Markovian dynamics that converges to this Gibbs state. So if you're interested in this, I would advise you to listen to Tristan's talk as well. And just to finish with two open questions, which I already mentioned before, we would like to know whether we can prove transport entropy for non-commuting Hamiltonians. So this would be very interesting for us. And the second open problem is the one of whether this dependence on the state in this Gaussian concentration I mentioned before. Sorry, where was it? No, it was after, sorry. Yeah, here. If the dependence on the state here is necessary or whether we can get rid of it. And yeah, that's the end of my talk. Thank you.
Okay, thank you, Cambyse. Thank you, Cambyse. Okay, since we are over time, so maybe we can take a quick question. Any questions from the audience? Okay, if not, then we suggest we can move to the Slack channel for further discussions. And now let's move on to
Sure.
the next talk.